Hello, everyone. Welcome to our next series on clean energy. It's geothermal energy, and I am your Professor Reena Randir. So the main learning objectives of our time together is for us to understand what geothermal energy is. So we'll study the basics and why it is important for the future of green energy. We'll talk about the different sources of geothermal energy, a very brief history of geothermal energy, the different types, the main pros and cons, and also the future of geothermal energy. So what is geothermal energy? Geo means earth, thermal means heat. So there is heat, inherent heat, that is found deep in the earth. So the earth as a core, it's called as the inner core, which is like 4,500 degrees centigrade, very hot. The outer core is liquid. The rock, it's so hot that the rocks have melted. Whereas if you see the mantle, it's a combination of both the liquid and rock. And the crust is where it is cooled enough so that life can exist. The picture on the bottom is depicting that the deeper you go down into the center of the earth, the hotter it gets. So when we harness energy from this heat, so the energy technologies that use thermal energy in order to make electricity, especially, is called geothermal energy. We've been using this heat for other uses also. So this heat has been around since the beginning of the evolution of Earth, and also because of radioactive decay of materials. So from the dense heat, intense heat from the core, the heat flows outward. And the crust is what is insulating us from the heat inside. So what is a geothermal reservoir? So these are natural trappings of heat in a pocket under in the Earth's crust. So they are naturally occurring areas of hydrothermal resources. So water can enter the crust of the earth through cracks. So when rainwater enters and it hits the very, very hard, hot rock, it vaporizes and it becomes steam, and it can get trapped in pockets in the crust. So these are called geothermal reservoirs. So this is a very, very powerful source of energy, because the deeper you go, hotter it gets. So some of the ideal conditions for us to use this energy is that it's accessible. So it is trapped under permeable or porous rock. So that is one of the deciding factors for the availability of this energy. Here's some examples of geothermal reservoirs. So this heat energy that is trapped under the Earth's crust is always trying to escape out. So there are three main ways it comes out. It's either through like volcanoes or fumaroles, which is a hole in the earth, and the gas and the steam will escape through it. Or it can be hot springs, where only liquid water comes out. And there's also geysers that shoot off hot water and steam. So this is Old Faithful in Yellowstone National Park. It faithfully erupts at certain intervals. And here's a few more pictures, hot springs, travertines, mud pots, fumaroles, geysers. So all of them are They are indicators of geothermal reservoirs underground. So a geologist will look for these things when he's doing a survey for building a geothermal plant. And we've seen this in National Geographic, this monkey. There are so many hot springs, and these snow monkeys are able to thrive in freezing temperatures because of the warm water. So where are these reservoirs found? They are highly concentrated in the fault lines. So here's the ring of fire that you can see that kind of surrounds the Pacific Ocean here. So here is the major tectonic plates. And this is where all the volcanoes, most of the volcanoes of the world are in this fault lines. And this picture is also showing how just 5% of the available geothermal energy is currently utilized. You can see the red bar. That red bar is showing the future potential of the energy in that location. But now currently, a very small amount of energy is trapped. That's why geothermal energy has a very promising future when the current energy demand is very high, and we are all looking for clean energy transition. So we want the energy grid to be replaced by clean energy. So that's why the potential in geothermal is very, very high. And here's the geothermal power generation capacity of the world, which is 15,854 megawatts in 2021. And you can see the top leading countries. The topmost is USA at 3,722, followed by Indonesia, Philippines, Turkey, New Zealand, Mexico, Italy, also Iceland and Japan are here. So they are the top producers of geothermal energy. In USA, so in this map, it shows the geothermal reservoirs and plants here. So everywhere you're seeing that intense red. So in the west coast of USA, you can see Oregon, Idaho, Nevada, Utah. So everywhere you're seeing the dark red, they are rich reservoirs of geothermal energy here. Also Hawaii. So here the geothermal energy is much closer to the surface. And also note, it's also closer to the fault lines. The largest geothermal reservoir in the world is in California. It is called Geysers Dry Steam Reservoir. No water, just dry steam is used for making an electricity. And there's at least like 20 of them. They have elaborated and enlarged that facility, and it's been going on since 1960. So the geothermal potential for US is tremendous. And here, this is an overview. Again, the deeper you go, the hotter it gets. And also the varied technologies. And there's also so much innovation that's happening regarding this now. So there are so many technologies to harness this energy. So here we have ground source heating and cooling at shallow depths. So, like 10 feet, 20 feet around this depth, it can either be an open loop ground heating pumps, or it can be a closed loop, or like here's the mine water, like abandoned mines, the hot water from the mines that are abandoned can be used. So they come under heating and cooling. And then the deeper ones that you see in the picture, that's going like 1 kilometer deep or 2 kilometers deep, is where we produce, where the steam and hot water is used for making electricity. So here, this picture shows about 5,000 meters or 5 kilometers. But if you go down to 10 kilometers, the temperature is around 200 degrees centigrade. A brief history of geothermal energy. So the heat that is escaping through the cracks and fissures on the Earth's crust was directly used for bathing. So since like 10,000 BC, there's archaeological evidence that showed, Romans and ancient Greeks, Maoris and Japanese and native Indians, and like the Qin dynasty in China, all of them using the hot water for like either bathing, for cooking, for preserving the food, and for also warming their homes. In 1892, the USA's first heating district in Idaho was built. But the first, discovery was made by Prince Pier Conti in Italy, where he converted the geothermal energy to electric energy and he lit some light bulbs. And then like in 1911, again in Italy, the world's first geothermal power was established. And here's a picture of that facility. So this is the first geothermal plant in Italy. It was destroyed during the World War, but it was rebuilt and it's still working now. And here's the world's largest geothermal energy, the Geysers dry steam in North California. And again, that is also going strong. The gas that's coming out from these towers, it's not pollutants. Like how when we see a coal factory, we would think it's polluting the environment, right? Here, this gas is only steam. So that's why the carbon footprint of a geothermal unit is very, very low. Another very attractive facet of geothermal energy is something called availability factor. So that means it is available all the time, 24/7, 365 days of the year. It is continuous, it's reliable base load power. So if you take solar energy, right, see it peaks during a certain time in the day. And also its efficacy changes over the different seasons. Same with wind power also. It's very fluctuating. Whereas geothermal energy is stable always. So the availability factor and the base load power is stable. It is very, very reliable. So it is, together they can complement each other very powerfully. So here is the availability factor of geothermal energy, and you can show that the reliability of geothermal is much higher when you compare to other renewable energy sources. Here, this graph is showing the greenhouse gas emissions from a geothermal plant is much, much less compared to any other like fossil fuels, like coal. Look at the amount of carbon dioxide emissions from a coal plant. It's 943 here. So this is the amount of grams of carbon dioxide per kilowatts of energy that is produced. And you can see natural gas, all of them are very, very high. Whereas if you come to geothermal power, it's very low. So the carbon footprint of geothermal power is very, very less compared to the other sources. It also has a very small land footprint. That means how much land do you need for creating a certain amount of energy? So geothermal energy, it has a very small land footprint. That means it can be set up in a very compact area and uses less land per gigawatt hours. It's only using 404 meters square. Whereas for the same energy, if you compare with coal, it's 3,642, and wind is high. Solar is also high. And here's a very good picture. And here in the picture, you can see comparatively, geothermal energy land use is very, very small, which is another very attractive feature for geothermal. So capacity factor. So this is what I told you earlier. This is geothermal energy is available all the time. It has an average capacity factor of 74%. The net capacity factor is the ratio of the actual electricity energy output over a given period of time to the maximum possible energy output over that period of time. So you can compare it. The most efficient, it looks like it's nuclear. We'll study this later in the semester. And then it is geothermal. It's much higher than when you compare it to wind and solar. Again, the levelized cost of energy comparison, again, it's very low for geothermal when you compare it with other energy sources. So when you say levelized cost of energy comparison, it's talking about the amount of money a project needs to make for every megawatt of energy it generates in order to break even. So this is a business kind of economy part of setting up the levelized cost of energy comparison. So it's like a profit analysis. So in other words, geothermal energy is very, very profitable over a period of time. So it has so many uses. It's not only just for energy production, but here in the picture you can see human beings have been using this energy for a long time, right? So here at lower temperatures, see like 40 degrees, it's been used for mushroom cultivation. So just the heat from the geysers or hot springs, and also maybe for heating a swimming pool, for using for aquaculture. And then at 65-degree range, it's been used for more things like vegetable drying in the industry, concrete industry, food processing industry, blanching and cooking and pasteurization. So for making energy for electricity, it's at higher temperatures. So from 90 and above, you can see all the pictures of different types of power plants. And here's the future of geothermal energy, which is to make green hydrogen energy production. We'll study this also later. And here's more interesting things of geothermal energy use. It's widely used for heating and cooling buildings up to, see, like up to this temperature here, from 40 to 150 degrees centigrade. So the uses are wide, and there's so many uses for geothermal energy. So it's classified, the use is classified in three basic categories. Direct is the low temperature that I talked about. So this is the heating swimming pools, or like even heating homes and greenhouses, aquaculture, paper processing, sterilizing, and milk pasteurization. So they all direct use of the energy. There's not fancy technology involved here. So we are directly using the heat of the water. So there's three uses, right? Direct use, ground source heat pump. So this is where you use for heating homes especially. And the third use is electric generation. So here's a picture of the underground heat exchanger. So this is called ground source heat pumps, GSHPs. So here you can see the heat from the ground will warm the fluid in these pipes. And the warm water will run through the house, heating the home. And in the summer, it is reversed, and it can be used for cooling. So here we see an example of geothermal energy used for heating and cooling the homes. So you can see this network of pipes that is entering the house, thereby transferring the heat into the house. A pump will be used to make sure it's pumped throughout the house. And here's the electricity generation part. So here the hot water is pumped from under the ground, and it's under high pressure. So when it reaches the surface, the pressure is dropped. And what happens is the water will turn into steam, and the steam will turn a turbine here. And when the turbine spins, the generator will make the electricity and then put it in the grid. And the water is cooled by a cooling tower, and then it is injected back into the earth. So this steam turbine, efficiency is only 15%, but there's a lot of technology going on to improve the efficacy. So here's an overall picture of the same that I just said. So hot water is pumped from underground and turned into steam in a flash tank. So the thing is, it's coming from high pressure into low pressure here, and then it turns into steam. And the steam will turn a turbine. And then that is attached to a generator that will make a lot of electricity. And then the electricity is transferred or exported into the electric grid. And the water, the leftover water, is cooled, and it is going back to the same reservoir. So that is why geothermal is sustainable. It's very, very sustainable. And here's another picture of the turbine and the generator. And this is what the turbine looks like. And this is what like a turbo generator looks like externally. So when you see this in pictures, you'll be able to recognize it. There are many types of geothermal resources. So here, volcanic and hot sedimentary aquifer, you can see they are much closer to the Earth's crust on top, right? So here, there's an underwater reservoir that is targeted. Both of them, hot sedimentary is also targeting an underwater reservoir, whereas if you see the enhanced geothermal system, it will drill holes much, much deeper to the hot rocks that are found deep in the earth to produce the electricity. So volcanogenic are relatively shallow, very high temperature, and high permeability geothermal resources. And it is usually close to volcanic activity areas. Hot sedimentary, a little deeper, fluid-filled sandstone or limestone reservoir, which natural porosity and permeability. So both of them have high permeability. It's about 2 to 3 kilometers from the surface of the earth, and the temperature can go up to 150. Whereas the engineered geothermal systems are the ones that drill very deep, 6 to 7 kilometers deep into the earth. The temperature is more than 200 degrees centigrade. And then that will make electricity. So there are 3 main indirect geothermal energy technologies. One is dry steam. So when you say dry steam, it means there's no liquid water. And this is the oldest type. So it's shooting up the steam up the pipes through a rock catcher and then directly into a turbine and then the generator. In flash plants, as I told you, so there's very hot water is coming from high pressure to low pressure, and in a tank called flash tank, it is becoming steam. So when the pressure drops, it becomes steam, and the steam will drive these turbines that drives the generator, and it is the electricity is transferred into the grid. So this is the also the most common technology and also the most efficient and very carbon efficient. It was invented in New Zealand. Here's a very good cartoon picture that clearly shows how it works. So water enters, and once it's done its job, it's injected back into the earth. Binary plant it's also very, very efficient because its carbon footprint is very, very low. So here there's one added step. So when you say binary means it's 2, right? So what happens is the heat that comes up from the geothermal water is used to vaporize something called working fluid. So it's usually isobutane or isopentane, which has a lower boiling point than water. And it's able to flash at a lower temperature to make steam. And then the steam will drive the turbine generator. So because of that 2-step process, it's called binary technology. And here we are able to use lower temperature reservoirs. And here's an example of a binary reservoir in Soda Lake, Nevada. So now what are the advantages? We've seen so many advantages of geothermal. It's clean, it's environmentally friendly, it's renewable. And as long as the earth exists, this energy will exist. It's the heat that is found in the core of the earth and below is what is sustaining life on earth. And also it's sustainable. It is reliable, abundant, and it's domestic. You're not going to import anything from anywhere. It does not require much maintenance. And we saw it's also used for heating and cooling buildings. Efficiency is high. It is independent of any meteorological variations. Capacity is high. It's not dependent on weather. Its cost of installing is currently, it's getting lower and lower, just like solar and wind, and thereby reducing the cost of production. And it also is very flexible. You can go for a modular setup, so that they can put one up, like in the California desert, and then you add on more to it to expand it. And there are lots of subsidies from the government currently because of the 2050 pledge to reduce carbon. The main disadvantage is location specific. It needs a suitable region, the soil porosity, the hot water, the heat aquifer must be closer to the ground. And initial cost of setup is very high. High cost of powering the pump. There can be noise pollution when there's drilling. And there's also concerns that it might cause earthquakes. And here's a very good example. So like a cascaded application of geothermal energy. So instead of putting the hot water after it's done its job to make its electricity, so this is Reykjavik in Iceland. They have used that hot water to actually heat the homes, to heat sidewalks, and also for regular water use in the home for cooking and bathing and all that. And here's the Blue Lagoon, which is a tourist attraction. And you can see one of the geothermal plants close by. So the water from the plant is like recycled and used by the entire city. And 95% of the buildings in Reykjavik are heated by geothermal water. And it's considered to be one of the lowest carbon foot cities in the world, cleanest cities in the world. So what is the future for geothermal? So here's a statement from International Renewable Energy Agency. They predicted that the output of geothermal energy in Europe can increase eightfold by 2050. Because of the technologies, a good site does not have to be in a fault area. Even Germany and Sweden, they're all like in this race to improve technology and to harvest this energy. The United States Department of Energy has pledged to increase geothermal energy by 26-fold by 2050, and hopefully providing 85% of the United States electricity, in addition to direct heat. And I hope all these things we learned today was clear and helpful for you.